All right, well, good morning, everyone. And thanks to the organizers for organizing this really inspiring meeting. So I will talk about a little bit about volcanic gases. And let's see, if we think about volcanic gases, we can look at two main things. One is like volcano dynamics, understanding what happens with the volcano. The other one is really to understand tectonic processes. So those are the two main categories that we tend to use volcanic gases for. Now, when we think about volcanic gases, what it really is, 90% of the gas is water vapor. And when that water vapor, the rest is CO2 and sulfur and all the other stuff. When that water exhaust from the magma at 5 kilometer steps, it's going to be a supercritical fluid. And then that supercritical fluid will cool and follow some kind of cooling path to the surface. And about 1 kilometer depth, it will become a vapor, essentially, and a gas. And then someone like Yuri Taran is going to be there, and sample it at the surface here, right? And that's what you did yesterday. So gas comes out here through a titanium tube, put it in a bottle, and then take it back to the lab, right? And so you hope for the best. But this actually, comes from really deep down, and you get the sample at the surface. This is from a gas workshop, IAFSA gas workshop, that's been going on for about 50 years or so. And the next field workshop is going to be in Peru later this year. So, all right, so some historical perspective. There is the gas sampling that I just showed that you did yesterday. The other thing that's really important in gas geochemistry is flux. And so one of the things we can measure is the sulfur dioxide flux. And there's been a major revolution in instrumentation. Before about 2000, we had to carry around this big instrument called the COSPEC that has this big telescope. You put it on your backpack, weighs 70 pounds, runs on a big car battery and a chart recorder. So you needed probably 3 people to do a traverse. And we've used it on a boat in Anataha. Since about, early 2000s, the mini DOAS came online, and it's much smaller, as big as, small cigarette pack or something. And since then, an instrumentation network has been put together globally to install these mini DOAS instruments to get continuous measurements of SO2 flux. So that's how we get sulfur dioxide flux. Multigas, you learned that yesterday, right? So there's a multigas network this is already outdated, but there are many multigas stations around the world on volcanoes collecting carbon-sulfur ratios for the most part. So that's the multigas station right here. And can we turn on the lights? And so then you have also cameras, right? So recently we have cameras, SO2 cameras, even infrared cameras that take snapshots of the plume, and you can just point it at the volcano, all afternoon and just collect the data, right? This is Sandra Yupa and his group in Papua New Guinea monitoring Manam volcano.
Really hard work there.
Very hard work. So then also you have other instrumentation, direct sampling, collecting different types of samples like the helium isotopes and copper tubes like you also did yesterday. And most recently, maybe drones have been used to collect some of those samples, right? So now if you think about limitations, well, these gas compositions that come out of the ground, they have one composition, right? That's the composition. And so every technique should have the same result. And that's not the case, okay? And we see, for example, this is from the Western Aleutians. This is diaryloid fumarole. There's some variation here. This is a different fumarole. But here, this is one fumarole. And there's a little bit of variation. And here's the multigas. And this is for another volcano, Kanaga. Here's the direct gas sample. So it's pretty good. It's pretty good. It's not perfect, right? But it only has to be as good as you need it to be, right? So like yesterday, talking about, what's the variation? So sometimes it's good not to overthink it, but try to like focus on what is it that you really want to answer. And for the most part, this is probably good enough, right? So again, this is from this gas workshop, where we can look at comparisons, different groups, sampling the same thing, and in general, it's pretty good, right? But there are some differences, and that's just the nature of the beast. Maybe it's going to get better over time, but that's just how it is. So those are some of the limitations. However, if you look globally and if you average some of these data, and this is a plot that Shinohara made a while back following Gegenbach style plots, CO2, water, sulfur, the three main components. And you see the CO2 sulfur ratios here from 20 to about 0.2, 2 orders of magnitude, right? And these are mostly Arctic gases, right? They show this kind of distribution. And then this is Erta Ale, which is a hotspot volcano in East African Rift. And it's kind of like a 2, 1, 2, something like that. So not vastly different from all the Arctic volcanoes, okay? Now, look at this, okay? This is POAS. And here's the CO2 sulfur ratio of POAS over time, like what, 5, 10 years, 7 years or something. So you see here these wiggles, right? Goes up and down, wiggle, 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 go up, 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 right? And so if you are here and if you have this data set, you're very excited about these little wiggles because wow, there's a lot of variation, right? And papers have been written about what this means, these changes in sulfur carbon ratio. And it has to do with the hydrothermal system of POAS. But then life goes on and boom, you get this drop of CO2 sulfur ratios of 4 orders of magnitude in a couple of weeks, right? So this is a message from the volcano. Pay attention to me, something really big is happening. Well, what happened was the dome was destroyed by the biggest eruption POAS has seen since like the 1950s, right? So big signal. That is then followed by a gradual increase again. These data, by the way, are taken by drone measurements for the most part, because all the instruments are destroyed. So that might be another limitation of volcanic gas geochemistry. All right, so in general, we could interpret this as a magma degassing trend. If the magma becomes more and more degassed, the CO2 leaves the magma early on, and you're left with more sulfur in the remaining gas. So one message here is looking at ratios is very useful. Looking at the absolute amounts is maybe a little bit more tricky, okay? Not working. There. Okay. So this general degassing trend, of course, can be modeled. And recently, a lot of information has been gained from using models like we've talked about, Solveig's Cossetti's model, magma to gas model, and so on, else, to understand, what does this gas composition mean in terms of pressure? Where is this degassing happening, right? And so if you look at these ratios here that are modeled 10 to 100, right? So you see that these ratios represent pretty low pressures. And you can plot them on this diagram and then kind of understand how has the magma moved, how has it degassed to produce the carbon sulfur ratios that you see at the surface. Now, you always have water, right? A lot of water. And so addition of external water, like meteoric water coming into the system, it's going to move everything kind of over there to that part. And so if you're interested in that aspect, you can look at the water sulfur ratio, for example, right? So it just depends on what you want to do. Like Terry already showed us, carbon sulfur ratios seem to vary systematically globally and have to do with the subtraction input. And this is Sandra Ayuka's work. And he did it, this is kind of the approach where he uses CO2, SO2, and then compared to whole rock barrier lanthanum ratios, which are traces for fluids. And then so the argument is if you have a certain carbon sulfur ratio, it has to do with slab fluid contribution, whereas if you have these very high ratios, it could be related to crustal carbon contribution, like Harry already mentioned. Now he extended this approach to the East African or to rifts, And with that approach, he was able to do kind of the same thing, looking at carbon sulfur, comparing it to whole rock data. And then through a lot of manipulation and extrapolation, he came up with the carbon content of the mantle that supplies these magnets. Right? So it's pretty interesting that you can use the gas composition and the whole rock data to get the carbon concentration in the mantle without having to really look at things like melt inclusions. Okay, and so this I'm just showing you to remind everyone that there are other gases in gases. So nitrogen, helium, argon, for example, but there's also methane and CO2 and CO, for example, right? And we see different trends for the continental rifts. We have this kind of trend here to low nitrogen helium ratios, whereas arc gases have very high nitrogen helium ratios. That's probably related to subduction of nitrogen. All right, now more specific volcano-oriented research. This is a very cool paper by Clive Oppenheimer, Ikmu Zalam, and others, where they use FTIR, right? So FTIR is a remote sensing technique. You need a lava lake as a light source, but you get huge amounts of data of all the gas compositions that can be absorbed by FTIR. So here, for example, this is Kilauea, and what they do, and that's very powerful, I think, is use the ratios of SO2H2S or CO-CO2 to compute an oxygen to gas, right? So that's pretty nice because, hey, you can get oxygen to gas in real time, right? And I think that's an important parameter for hydrologists. So oxygen to gas, you can get that in real time. What they found is that during vigorous degassing, the gas actually diverts a little bit from a buffer that is dominating the gas composition during mild degassing. And so what they interpret this as, and compare it to the type 1 and type 2 gas of burlap collected with direct sampling back in '83, they compare it to that and interpret it as essentially during the times of vigorous degassing, the gas melt system is out of equilibrium. And so, the larger bubbles, they cool faster and therefore are out of equilibrium with the melt. So the volcanic dynamics have an effect on the oxygen fugacity that you get from the gas composition. So if you can quantify that, which they do in the paper, you can learn something about the magma dynamics during these different parts of volcanic degassing at Kilauea. Now, going back to more global things, yesterday we talked about diffuse CO2 degassing, and this is a compilation that we did to look at all the volcanoes in the world that we have data for, and then extrapolate to the 500 volcanoes that we think are degassing, but there are about 900 volcanoes total that may be degassing, okay, but maybe not degassing right now. So anyway, Yellowstone would plot about up here, right, way up here. So one of the biggest CO2 emitters in the world. Now, why am I showing this? Well, most of the CO2 in the world from volcanoes is emitted from about 10 volcanoes. And then, the next 100 emit about the same amount, and then all the others emit much, much less. And there are a lot more of them, but they emit very little. So the top 10, this is like a race. This is like the race over the history of the Earth. Who's going to be at the top? And that top is always changing, right? At this time, it was Abrim was at the top, Etna was second, Bargana, and Kilauea is up there. Kilauea is not up there right now. It's not degassing very much, so Kilauea might be down here. So it's always moving around, right? So it's just a snapshot that we have. And we have to keep that in mind, right? When we do things like this, okay? So here is where we have volcanic plume degassing, diffuse emissions, and then tectonic degassing coming up with the CO2 budget, and then comparing it to Terry's subduction input estimates and trying to balance the carbon budget, right? So this is an approach that's super useful because we want to understand the carbon budget of the Earth. But again, from the gas perspective, it is definitely only a snapshot of today, and extrapolating those things back in time or into the future is challenging, and certainly is a limitation of kind of gas geochemistry. Again, going back to Kilauea, I just want to highlight this really interesting study, I think, where they do the same kind of thing where you have CO2 emission rates from Kilauea, and then you use a model of magma production per unit time. Okay, so if you have the CO2 emission, if you have the magma production rate from another source of information, you can essentially get at the anti-gas magmatic CO2 concentration that supplies the magma to Kilauea, right? It's a straightforward thing here, done very elegantly with a complex model. But essentially, you get the anti-gas magmatic CO2 concentration, and that's what we talked about 2 days ago. But what is it? It's about one weight percent at Kilauea, for example, which means that this magma would become saturated at about 30 to 40 kilometers depth. So, it's degassing CO2 quite deep, okay? Supercritical fluid, again, there's not just CO2 in it, probably going to be water in it, which might degas at a little bit shallower levels and so on. Okay, so let's skip over that. So in terms of going forward, yesterday we had a really nice time being in the shade, doing like a CO2 thing, right? So you wait 2 minutes to get data point. But if you actually wanted to know the flux of CO2 from Yellowstone, it would be a lot of very, very hard work, right? You'd have to crawl around everywhere and get all these data points. And then also you'd have to get all these permissions to work in a park and all that stuff. So what we've been trying to do is we've been trying to use drones to do this work. And it's something that drones should be able to do, because essentially the CO2 plume goes out into the air, right? Goes up into the air. And so what we have done is we just put a sensor, like the same sensor that was in that diffuse degassing box, or in the multigas, in some multigases, slap it, like put on a drone there, right? And so we have 3 drones here flying in a swarm. And this is in the Jemez Mountains in New Mexico. During the pandemic, we couldn't leave the state. So this is where we went, did all of our experiments. And so the drones, they are programmed to find CO2, right? So they fly up and then they do this lawnmower thing, we call it lawnmower, which is mow back and forth, but there are 3 of them. And so the 3 of them, they can detect much closer CO2. They can fly more because there are 3 on one single battery. So you can cover a pretty big area, and you can find CO2 where there's high CO2 concentration in the air, right? And it's not very much, but the sensor is very sensitive. And also the drones can be programmed to find the CO2. It's like gradient descent. So find the source. There is most of the CO2 coming out. And this we just published recently, this kind of approach. Now we need to go from this. This is very nice because it's a nice map, but it doesn't tell us the CO2 flux, right? So it's not useful for me. I want to know the flux. And so we're working on that, and I hope we get there at some point. So here is, we went to La Palma, which is really cool. After doing no field work, the volcano erupted, and we were able to go there to the La Cumbre Vieja eruption. And we were flying the drones through there, through this eruption column, ash column. And I was amazed by the data we got, because we just transect the plume. You see it's pretty far. It's like 1,000. It flew like the drone flew almost 2 kilometers out. Totally line of sight, of course. So you fly along, and then the CO2 goes up, and then you go out on the other side of the plume. It's a beautiful Gaussian distribution. And so what we do, we fit the Gaussian to that, and we flip it essentially, assume double Gaussian, and then get essentially a slice of the plume and get the concentration of CO2 in that slice. And then from that, we should be able to calculate the flux. So we're kind of working on this. I hope we can get there soon. So this is just something we're working on right now. At the same time, we collect a gas sample with the drone. So this is actually from Taburgo volcano in PNG. Fly in, collect the sample. Like yesterday, I showed you we collected the back sample from the diffuse flux meter. Same thing, you just have the drone fly in there, suck some gas into the bag, and then you analyze it on some kind of mass spec, and you can just collect the samples. This is from the drone. This is a flank fumarole collected by hand. This is a hot spring. And then you can simply extrapolate to the composition of carbon. This is carbon isotopes here, and you get the composition of the carbon of the source of the gas, right? So instead of going there, collecting the sample by hand, we try to do it by drone, much safer, and getting to places that are maybe not accessible. Taryn and I did this in the Aleutians by helicopter, and we flew the helicopter to Canada, collected these samples. And what we found was also that if you circle around the volcano too often, you actually just sample helicopter exhaust. So this is, the drone is helpful in that regard. Okay, fluxes are super important, I think, for volcanic gases because it gives you that time perspective. Here's a very nice work for helium isotopes and helium fluxes. People were asking about this yesterday. This is El Hierro, again, nice time series. And here's diffuse helium emissions, right? And I don't have time to talk about how they did this, but you see a helium emission going up before the eruption, and also the 3-4 ratio, which is a really good indicator of mantle-derived gas, increases before the eruption, drops down, and increases again. So this is extremely rare data. Getting helium fluxes is challenging to get, but it can be super useful. Okay, and it correlates with seismicity and so on. What it requires, though, is you have to take your helium sample in the copper tube and take it to a lab, like Pete Barry's lab. And you've seen some very nice data from Mike showing nitrogen and helium here in a poster. It's a big lab, and you can run about 4 samples per day, which is great. 4 samples a day is actually really, really a lot. But we want more, right? We always want more. So here's Gary's gizmo. And this is a helium analyzer that he's put out in Hawaii, and it can theoretically run in the field, but you need a lot of power. You need gas, for example. So it's not super portable, but at least you can run it in the field, and you can get data in real time. And this is just some preliminary data that I'm showing you here. We're trying to get this published. But here's some helium isotopes, flat, and then goes up, from like what, 4 to 15. If that happens, the volcano is telling you, pay attention to it. I'm doing something. You should be measuring this, right? And so it goes up, and then the eruption happens. Okay, so this can be very, very useful if we can get enough data again. And so, if you collect a few samples every few years, you might miss some of this stuff because you just don't have the sample. Okay, so that's a current limitation. So more gas data, more continuous gas data is definitely a goal for us and has always been, right? And we're getting some really exciting new things with the DAS. There's a very nice study in Yellowstone Lake where they use this fiber optics cable to detect bubbles, and then from the bubbles you can figure out the gas flow. So that's pretty cool. And this is again just the drones are helpful because you could send drones to get more data. And this is just again from Emma Liu's work, where you flying through the plume, you get SO2 increasing, flying back, flying through. So you get these SO2 concentrations. From that you can get the SO2 flux, but you can also get the ratios of gases from that inaccessible plume, right? And so then you can use that data to make a plot, like our plot here. This would be Manam, ratio of 1. Hey, is that magma pretty gas? Looks like already pretty gas. But what is it going to do in the future? How is it going to change? And so it allows us to get data that we were not able to get before. It makes things possible that weren't possible before, because you can't climb up to Manam volcano. Okay, I'm going to skip this one. And I just want to remind you that the rifting community also has an interest in volatiles, right? There is understanding the role of fluids as a big part of the rifting community. And there was a meeting, R2R 2021 workshop. So more information is coming out on that workshop, on those results. So it's not only arcs, there are also rifts, which are important parts of the Earth system. And there's a lot of interest in fluids in rifts as well. So with that, I thank you.
I was curious, I know that with monitoring, you need like all the different tools because sometimes some will show something and some won't. In gas community, like looking at this helium data, if you looked at, CO2, SO2 ratios, would you see the same kind of evidence like volcano wants you to pay attention? And, do you have more faith in a continuous measurement of certain gas species than others?
Yeah, absolutely. Great question. So, if the CO2 sulfur ratio changes because of a new magmatic injection event, then the helium isotope should show the same thing, right? So ideally, these things would show the same kind of process, right? But most of the time, we don't have all that data. So we don't actually know, but in theory, it should, right?
Yeah, I was just curious because it seems like helium's like much more challenging. So I was curious, like, why go there?
Oh, much more challenging. Yeah. Why go there? Very good question. Because Kilauea, for example, that fumarole sulfur bank is very low temperature, and it doesn't emit any SO2. Of course, you could monitor the crater, but there the gas is very dilute, right? Until it gets to the crater rim, where you might have your multi-gas station. So you might not see that signal as well. There might be something's happening between the gas escaping the volcanic vent, and by the time you measure it for the multi-gas. So it just really depends on the volcanic situation. But you're absolutely right? So for most places, probably a carbon sulfur ratio would be fine. Right? Yeah. Yes.
I have two questions, Tobias. One was for your drones.
Yeah.
Do you put the particle collectors on there?
We don't, but we could.
Okay.
Yeah, we could.
And then the second question is more of a technical question, but how do you actually collect the gas? Like your drone doesn't have a helium flow.
No.
So I'm assuming you're using a gas bag, but then how do you collect